Imagine your multi-agent pipeline ran 6,000 requests last month. The bill arrives $2,400. You budgeted $160. 3 design decisions made before line 1 of code determine whether that number is $20 or $2,400. This is what they are. Every multi-agent pipeline has a cost structure nobody warns you about, and it has nothing to do with how much the model charges per token. It has to do with how many times you pay for the same tokens. Here is what happens in a typical orchestrated pipeline. You have a coordinator, one Claude call to plan the work. It spawns 5 subagents. Each subagent makes its own API call. Each one sends the full system prompt, the full tool definitions, the full shared context. 50,000 tokens that haven't changed between calls sent 7 times. At $5 per million tokens for Opus input, 50,000 tokens costs 25 cents per call. 7 calls, $1.75 just in system prompt tokens for a single user query. At 100 queries per day, that's $525 per month in system prompt tokens alone. Tokens that represent context nobody asked you to resend. This is the cost multiplication pattern in multi-agent architectures, not a bug in the design. A consequence of treating every API call as independent when they all share the same knowledge. The 3 levers we're about to cover attack this at its root, not by cutting context, by designing for how the API actually prices repeated work. The first lever is prompt catching, and it changes not just what you pay, it changes what you can afford to send. Here is the mechanism. When Claude processes your request, it can store the processed version of your prompt prefix in a key value cache. Subsequent requests that start with the same prefix, same tools, same system prompt, same conversation history up to a cache breakpoint, skip the full processing and read from cache. Cache reads cost 10% of the standard input price, not 90% off. 10% of the original price. That 50,000 token system prompt that was costing 25 cents per call. First cache call, 31 cents, you pay 1.25 times to write. Every call after, 2.5 cents. At 100 calls per day, that's $25 per day without catching. $2.53 with catching. Per month, $750 versus $75. For context, that never changes. There are 2 cache durations. 5 minutes costs 1.25 times to write and breaks even after exactly 1 reread. 1 hour costs twice the base price to write and breaks even after 2 reads. For system prompts serving many concurrent users, the 1 hour cache is obvious. For conversation history where each thread is unique, 5 minutes is usually enough. The break-even math is simple. Pay a little more on the first write, get 90% back on every subsequent read. After 1 hit on a 5-minute cache, you're ahead. After 2 hits on an hour cache, you're ahead. And then you stay ahead for every call within the window. Adding cache control to your system prompt does not guarantee cache hits. The reason teams get 20% hit rates when they expected 90 is almost always the same dynamic content bleeding into the cacheable zone. The cache operates on prefix matching. The entire prompt up to your cache breakpoint must be identical across calls. 1 character different, 1 variable injected, 1 timestamp changed, cache miss. The hierarchy is tools first, system second, messages last. If your system prompt includes a username, a session ID, a timestamp, the cache busts on every single call, even if 99% of the prompt is static. The canonical pattern is simple. Tool definitions, static, mark for cache. System prompt, static context, mark for cache. Dynamic user content, at the message tail after the last breakpoint. The dynamic tail does not need to be cached. It changes every call. But the 50,000 tokens of static context before it, cache those, and they cost 2.5 cents per read instead of 25. When your cache hit rate is low, and you don't know why, Cache Diagnostics removes the guesswork. Pass the previous message ID in a diagnostics field on your request. The API returns a cache miss reason, the exact position in the prompt where your prefix diverged from the previous turn. Not a generic cache miss. The specific location. This transforms cache debugging from a 3-hour debugging session into a 5-second diff. The metric to instrument is cache read input tokens divided by total input tokens. That ratio is your cache hit rate. If it's below 80% on a high-frequency agent with a static system prompt, you have a prefix architecture problem. The usage response gives you both numbers. Instrument it from day one. Half your AI spend goes to work that didn't need a real-time response. The message batches API is exactly one change to how you call the API. Instead of calling messages.create and waiting, you call messages.batches.create with a list of up to 10,000 individual requests. Anthropic processes them asynchronously. Most batches finish within 1 hour. All batches finish within 24. When processing ends, you retrieve a stream of results. The discount, 50% on all input and output tokens, every model. At Haiku 4.5, the batch price is 50 cents per million input tokens and $2.50 per million output. At Sonnet 4.6, $1.50 in, $7.50 out. At Opus 4.7, $2.50 in, $12.50 out. These prices stack with prompt caching. If you also have cache hits, you're applying the 50% batch discount on top of the 10% cache read price. The batch API is a forcing function. Any workflow you can restructure into collect, then batch, then retrieve was, by definition, running synchronously by accident rather than by necessity. The question to ask before building any AI feature, does the user need this result in under 1 second or in under 24 hours? Only the first question requires a synchronous call. Large-scale evaluation runs, content moderation queues, bulk data enrichment, nightly report generation, test suite scoring, all batch eligible. Conversation turns, tool call responses, user-facing recommendations, not batch eligible. The discipline, categorize before you build. You routed everything to Opus because you didn't want to debug quality issues on simpler models. You've been paying 5 times the necessary price on most of your calls. The model tiering decision is about matching task complexity to model capability. Haiku 4.5 is $1 per million input tokens and $5 per million output. Opus 4.7 is 5 times that on both. The question is not which model is best, it's which model is sufficient. For classification, extraction, format conversion, structured output with a clear schema, Haiku. For most reasoning tasks, code generation, complex tool use, Sonnet. For tasks where quality materially changes the outcome, complex multi-step judgment, novel research synthesis, ambiguous calls where wrong is expensive, Opus. Anthropic's own guidance from the pricing documentation, Haiku for simple tasks, Sonnet for most production workloads, Opus for the most complex reasoning. The operative phrase is most production workloads, going to Sonnet, not Opus. Here is what routing does to a 6 subagent pipeline. Without routing, 7 Opus completions, coordinator plus 6 subagents, blended input cost, $5 per million. With routing, 3 Haiku for extraction and formatting, 2 Sonnet for reasoning, 2 Opus for synthesis and coordination. Blended input, 3 times 1, plus 2 times 3, plus 2 times 5, $19 across 7 nodes, divided by 7, $2.70 per million. 46% reduction in blended input price. No quality change on the non-reasoning steps. The routing function itself is 10 lines of code. A task type field on the tool call, a lookup table mapping task types to model strings, and a default of Sonnet for anything unclassified. The hard work is the audit, deciding which tasks in your pipeline actually need Opus reasoning and which ones just feel like they should. Each lever saves money. Together, they change what you can build. Here's the compounding. Start with Haiku 4.5, $1 per million input tokens. Apply the batch discount, 50 cents per million. Apply a cache read, 5 cents per million input tokens. That is Haiku batch plus cache read, 5 cents per million. Against standard Opus at $5 per million, 100 times cheaper on cached input tokens. Run the numbers on a production pipeline, 10,000 agent queries per day. Each query, 1 coordinator Opus call, 3 Haiku subagent calls, 50,000 token shared context cached, 10,000 token unique content per call. Without optimization, $175 per day in system, prompt tokens at Opus standard rates. With all 3 levers applied, system prompt cached at Haiku batch read prices, subagent calls routed and batched. Roughly $6 to $8 per day, equivalent throughput. Same quality on synthesis steps, 95 to 97% cost reduction. This is not theoretical. Prompt caching exists because production agents with large stable contexts were not economically viable without it. The batch API exists because a 50% discount changes the unit economics of bulk AI workloads. These are production tier features, not experimental ones. The design space opens when the per call cost drops to cents. Architectures that were unprofitable at Opus standard pricing become profitable at 5 times cheaper base tier, 10 times cheaper cached input, and 2 times cheaper batched. There is a fourth dial, one that lives inside Opus itself. Extended thinking lets Claude show its reasoning before answering. Those thinking tokens bill at output token rates. For Opus 4.7, $25 per million output tokens. A 32,000 token thinking budget on a call that uses 12,000 tokens of reasoning costs 30 cents per call in reasoning overhead alone. At 100 calls per day, $30 a day, $900 per month. In reasoning that may or may not be improving your results. The budget tokens parameter is the control. Set it to 0. Standard mode, no extended thinking, full speed, output tokens only for the actual response. Set it to 4,000, light reasoning for summarization and code review. Set it to 32,000, deep synthesis for multi-step research and complex judgment. Most agentic loops have a mix. Routing calls, format conversions, classification. Budget tokens 0. These tasks do not benefit from a chain of thought. Summarization, plan generation, code review. Budget tokens 4 to 8,000. Novel research synthesis, complex multi-step judgment. Budget tokens 16 to 32,000. One budget cap for all task types means paying full extended thinking prices on calls that don't need it. The same routing function you built for model tiering applies here. Task type maps to model tier, ANT to budget tokens. Same 10 lines, 2 outputs. 4 levers. Each one a design decision you make before the first pull request. Lever 1, prompt caching. Cache reads cost 10% of the standard input price, up to 90% off repeated context. The design decision, structure your prompt so static content, tools, system context comes first. Dynamic content at the tail after the last cache breakpoint. Lever 2, batch API. 50% off all tokens for async processing. Up to 10,000 requests per batch. Results within 24 hours. The design decision, categorize every AI feature as real-time or async before building it. Only the former needs a synchronous call. Lever 3, model tiering. Haiku at $1 versus Opus at 5, a 5 times difference in input cost. Identical quality on non-reasoning tasks. The design decision, define which task types in your pipeline need Opus, which need Sonnet, and which Haiku handles, and build the routing function before you route anything. Lever 4, token budgets. Budget token 0 disables extended thinking entirely. Match the budget to the task complexity, not to the hardest task in your queue. The design decision, never use one budget cap for a mixed task queue. Combined, 3 to 5% of the cost of a naive Opus everywhere synchronous pipeline with no caching for the same quality where quality matters. The cost is in the design, not in the discount you negotiate. In the architecture you build before line 1. Subscribe to AI Tech Book for the next video, Opus, Sonnet, or Haiku, choosing the right model for every task.